Okay, ready? Hello and welcome to the introductory lecture for introductory astronomy at Michigan Tech. It's called Physics 1600, PH 1600 for people who are into letters and numbers. So this is the first class. Today we'll be doing a tour of the universe. But first we have boring stuff to talk about related particularly to the courses taught at Michigan Tech. I will say that these lectures are being recorded, and as within the past 2 years, these lectures are generally available over the internet. They're available over iTunes, and over the past couple of years, they've been available at a website called learnoutloud.com, and it's no breaks, and it's spelled as it sounds. And so I've gotten email from places like China and Kansas from people who have followed versions of this course. And it is partly because of that audience that I'm going to be doing the course in the way I'm going to be doing it this year, which is making it free in the sense that it doesn't cost anything to buy the materials for the course. This is going to be an entirely online contained course. So you never have to come to class. Although there is if you're taking this at Michigan Tech, there is reason to come to class because, as I will show in the syllabus, if you bring a question about, or you formulate a question about the material and you hand it in during class or after class, would be appreciated. That question may be incorporated on the quiz or on the midterm or the final. So there is value in coming to class this year. But if you're following this from Kansas or China, or you just don't want to be bothered to come to class, which is fine, people are busy, you can just download the lectures from iTunes or Learn Out Loud. You can take the quizzes online, and you never have to see me again. And if we pass in the hall, you can just look the other way, pretend you don't know me. That's fine. You can still get an A. It's happened. So I usually start the lecture out with a picture of something that it is not obvious what it is. One of the neat things about astronomy is that it's a big universe out there, and we don't know what much of it is. And so there's some really interesting pictures that are taken, and it's interesting to just contemplate what is that. And so I will start almost all lectures, including this one, with a what is this, where I just show you something, as you see on the screen. And maybe if you're an astronomy buff, or if you've been following the astronomy picture of the day or something, you might know what it is. But I will tell you for an extra fee, I will tell you for free during the class were you to watch the whole lecture. If I forget and it looks like I'm wrapping up, please feel free to raise your hand and tell me. So I said, this lecture is Grand Tour of the Universe. There's lots of preamble today. So if you're watching this on the web, move the little slider across so you don't have to listen to this, this boring stuff. This university is Michigan Technological University, which is in the beautiful Keweenaw Peninsula of Upper Michigan. I'm your cosmological coordinator, Professor Robert Nemiroff. There will be 2 TAs, at least, as I know them, to help with this class. Both are undergraduates, Ashley Ames and Martin, and I have never pronounced his last name, although I've seen it many times, Bolette. Okay. And this is happening live right now, for me anyway, in the fall semester of 2008. A big change with the past way this course has been taught is that there will be no formal book. We're going free this time. So the Wikipedia pages on astronomy, particularly introductory astronomy, are really good. So we're going with the Wikipedia pages, and I will list exactly which ones they are. Now you might say, I know what to do. I'm going to go to that Wikipedia page and change it to one word which says blah, and then all I'll need to know is the word blah. But that won't work, because what you're responsible for is the Wikipedia pages as they appeared yesterday. So going into Wikipedia and editing it now won't work. Now how do I get to yesterday's page? If you type in astronomy into Wikipedia, you're brought to the current page. However, if you go into history, which is one of the tabs on Wikipedia, you can find out the page that is closest to yesterday, occurred before yesterday, and that's the one that you're responsible for. There is going to be very little changes. Most people aren't going to go in and try to make big changes because of this little puny class. So you're probably okay. But if you have any questions about the material, if you think you're seeing something on Wikipedia that's not right, go back to the September 1st or 2nd page. If you still have continued questions, what you want to do is you want to send email to ph ph1600@mtu.edu. There will be people monitoring that web address all the time. PH stands, this is the title of the course. PH1600 is the Michigan Tech designation for the course. So I have access to that email address, but I'm too lazy to monitor it that often. The TAs have access to it, and they will be monitoring it more often. If it is above the TA level, if it deals with something, a question they can't answer or something like that, they will alert me to go there and look at it. So, so I will ultimately be responsible for what's there. You'll see that address many times. If you're taking this course at Michigan Tech, you have to go to courses.mtu.edu. So if you're a freshman just learning that, a lot of your courses you'll find online there. They will have syllabus, plural of syllabus. They'll have other wonderful things that I can't even mention here, partly because I don't know what they are. We can do that right now with the miracle of modern technology. We can go to the Blackboard learning system here, and here you notice up at the top it says courses.mtu.edu. That's where you go. Then you're going to be asked for your Michigan Tech login and password. If you don't have one of those, I'm not the person to ask about that. You need to find your faculty advisor or some really smart kid at the end of the hall who seems to be well connected and ask them how it is they're getting into the Michigan Tech pages. Then they'll tell you, and then you can pretend after that that you've known it all the time. That's what I do. Let's go to the syllabus here. Page contains both secure and non-secure items, so please beware. Let's display it anyway. All right, so anyone can monitor this course online, anyone. However, that's free. To actually get college credit, well, that's going to cost you money. So if you want the college credit through Michigan Tech, be sure to pay Michigan Tech or have your parents or some close relative pay us. You can get the information for free. You could have gotten the information for free anyway. You didn't need to take this course. You can go to your local library anywhere and take out lots of books on astronomy and read them. You can go to Wikipedia and read the online astronomy pages. You can follow the astronomy picture of the day for free. The information was always there. It's the college credit that you have to pay for. As I said, I'm going to be repeating things. So I'm a big fan of actually repetition. I feel that if I repeat it many times, I, for one, will remember it, and other people might remember it too. So I'm happy to repeat things. And this class, you'll see that the important stuff hopefully gets repeated more than once. So class attendance is optional. As we said, you don't need to see me or these obnoxious people ever again. However, students are encouraged to attend the in-class sessions, and they will be right here where the students in class are. Riki G005 for people who are within commuting distance, and they will be on Monday and Wednesday from 10 to 11. Really 10:05 to 10:55, but that doesn't look good when you put it up there. If you arrive at 10, we're fine. You can even stay 5 minutes late and chat with your friends. Students attending class will be given the opportunity each class to pose a question that may appear on a quiz, midterm, or final. So unlike last couple years where there was really no benefit at all to coming to class, I'm trying to make a benefit to coming to class this time so people can be a studio audience. Let's see, as everything can be downloaded, cheating policy. So how can this possibly be a good course if you can do everything online? I mean, you can just get someone. You can call up your friend's uncle who used to work at NASA and get them to take your quizzes. Well, yes, but you would be violating the cheating policy. The cheating policy says that you can use open notes, open web, and open video lectures. You can play the video lectures as much as you can. You can bring up other windows on Wikipedia as much as you want. But you cannot do open people. You need to take the quizzes and tests by yourself. Now, we have ways of checking on this. One of these is we can find out when people are taking these, how long it takes people to take them. There are online ways of checking, and there are also human social engineering ways of checking. The people who you think you're trusting may be asked in a questionnaire whether they've taken this test alone. And then you can trust them for sure. But let's say they end up on the at the honor board and they have to save their own hides. They might not be willing to save yours. That happens a lot on Law & Order, you might notice. People in the beginning of the Law & Order episodes, they're always quite sure they can get away with it. But by the end, they're pretty much ratting on their friends. So watch out. So do this by yourself. Lectures will be posted every Monday and Wednesday before 4 p.m., probably around 4 p.m. We'll try to have them on there, as will the quizzes. So the quizzes will be posted on Wednesdays, and they will be due on Monday. I think it's Monday at 4 or 5 p.m. Again, going to courses and clicking on the right tab, clicking on the assessment tab here, will bring you to the quizzes. There should be a quiz online now, but I haven't finished it yet. But it will be available by 4 p.m. I am the instructor. Here it says in the syllabus. The teaching assistants are, as I showed. All email regarding the course goes to ph1600@mtu.edu. The grading is very simple. You take the online homeworks, quizzes, and final, and if you get between a 90 and 100, you get an A. If you get between 80 and 87 to 90, you get an AB, and so on. You have to do lower than 60, actually 59.5, in order to fail the course. And although we get generally relatively good grades, there seems to be just about every semester someone who doesn't take the course seriously enough to fail. This is not a difficult course. There might not be a textbook, but astronomy is, a lot of stuff you can look up. It's a lot of stuff thinking about where we are in the universe. It's, I think, within the realm of everybody within my earshot. You can do this. You just have to spend the time, which is one of my big lectures in that in the beginning of the semester, and during the semester, you have a currency which can buy you good grades. And this is true for every course, not just this course. And that currency is time. If you try to do the quiz at the last minute, you have very little currency to buy yourself a good grade on that quiz. Your time is going to run out, and before you submit it, the time will have run out, and you won't get credit for the quiz. And you have to send one of those pathetic emails saying, oh, please, my grandmother and 12 other people died, and on the way to the funeral I was in a car accident and couldn't get it done. And that might work once, but it's not going to keep working because you only have one grandmother. So use your time. You start early when you have hours, and you can do this. Go to the pages, complete the quizzes, check things out, do little calculations on note paper that you find. You can do this. This is not that difficult. Here's topics and when they will be covered. These are all Mondays and Wednesdays. September 3rd, which I'm told is today, 2008, which I'm told is today this year. So we're going to do a quick grand tour of the universe. Then we're going to talk about light, matter, energy. We're going to go through the inner solar system, the outer solar system. We'll talk about Pluto, which has made the news a lot. We'll have a midterm. We'll talk about then. That's pretty much the inside the solar system stuff. Then we're going to branch out into the universe. We're going to do stars. We're going to do our star. We're going to do distant stars. We're going to travel to black holes. We're going to look at our galaxy here. We're going to talk about the universe as a whole. We're going to go to the beginning of the universe and find out what we think happened there. And we will last talk about life in the universe and where to find it. Okay, back to the PowerPoint session already in session. Okay, so again, this is not required, so going to the next thing. So what is one of the goals of this course? One of the strengths of this course, I think, are the two strengths. One is that this is what I think of as a beautiful astronomy course. There's tremendous amount of beautiful images out there, all kinds of beautiful images out there, many of which are very educational. And we're going to try to highlight them as much as possible. Now, this doesn't mean it's going to be a lightweight course. It's going to be rigorous. It's going to be college level. There's going to be calculations to do. But as much as possible, because there's so many amazing images out there, I'm going to be liberally illustrating the lectures with pictures that have space themes. I can do that partly because I am one of the two people involved in creating a popular astronomy website called the Astronomy Picture of the Day. That's typically served out of nasa.gov. And so I'm very familiar with what is on APOD. I'm very familiar with all the pictures. Astronomy Picture of the Day is abbreviated APOD and pronounced APOD. There should be a T in there, but it sounds strange if you try to pronounce the T in Astronomy Picture of the Day. So anyway, so we're trying for a beautiful astronomy course. Also, we're trying for a free astronomy course so that this will be recorded. Hopefully lectures will be available through this semester and also rerun possibly through Learn Out Loud, iTunes. And so people, if they want to follow from, as I said, Kansas or China or wherever, they don't have to go buy the book. You don't have to have a lot of money. Also, introductory astronomy books have a tendency to cost a lot of money. And I'm trying to save students some money by saying, essentially everything's there on the web. You don't really need, the textbook cartels are particularly strong in some areas, but you don't really need them in astronomy anymore because the web is so strong. Textbooks are essentially, were very strong and were dominant in maybe the late 1900s. But in the early 2000s, many times they're going to be going away. The web is just too powerful. It's taking over. So let's start here. This is the first class I know of that's just abandoning the textbook in favor of the web. Probably has happened before, though. I just don't know about it. Again, this is a rigorous course. Just because it's beautiful and free doesn't mean it's not rigorous. You're going to learn, if you stick with this, if you take the quizzes, the midterms, and the finals, you're going to be learning a lot of astronomy. Typical of a college-level U.S. astronomy course. Okay, reviewing, yes. So the pictures are, almost all of the pictures, not all, will be chosen from Astronomy Picture of the Day, which is at apod.nasa.gov. That's listed when you go to the course web pages, too. It's freely available to anybody. One of the neat things about using APOD images is that there's advantages to the web over textbooks. Textbooks are printed at a certain time, and that time is usually months before a class starts. But particularly a fast-moving science like astronomy doesn't stop. There's constantly new images from Mars, from Saturn, from the Hubble Space Telescope that are coming down. We can use those in the course. Even if they're taken during the course, we can use them, and we will be using the most recent images that aren't in any textbook that's published at the beginning of the class. Also, as I said, there's some just truly amazing pictures, and we'll be describing those pictures in some detail. Again, it's free. Wikipedia has become relatively strong. Wikipedia is free and advertising free. And again, information is free, but diplomas cost money. So if you actually want credit for this, you have to pay somebody. In this case, Michigan Tech. What are you responsible for, given this somewhat, well, here it is. You're responsible for the lecture material. These lectures occur in person now, and in most times you just go to lecture, and once the lecture is over, it's in your memory, and a little bit on your notebook, and then it's gone. But that's not true of this class. This class can persist even longer, possibly longer than you want it to, because you can just go to the web and play back this lecture again and again and again until the people in your hall think there's something strange. You can always go to the Wikipedia pages. They're always online. As I said, we're keeping the Wikipedia pages as they were on September 1st. At the end of this lecture, on Wednesday lectures, I will be reviewing the astronomy pictures of the day for that week. We will be, at the end of this semester, you will be responsible for the text, not the links, the text of all the astronomy pictures of the day between September 1 and December 15. You are responsible for the very explicitly stated set of Wikipedia pages. So this lecture, I will be giving you what Wikipedia pages you're responsible for. You're not responsible for all Wikipedia. It's just too big. No one's even read it all. You're also responsible for completing the quizzes. Even if you watch the lecture, we know when the lectures are downloaded, assuming you go from the website and not learn out loud. But to get credit, you need to complete the quizzes. And you have to do them on time. So the Wikipedia entries of today that you are responsible for are, just type in your Wikipedia English search box. This is English, of course. Universe, electromagnetic spectrum, and light year. And if you forgot to write this down, just watch the lecture again and write it down then. And that's the Wikipedia stuff and the stuff that I mentioned in this class. Okay, so I'm going to go over to the cosmic questions. So this is beginning the tour of the universe. So this is actual content. So in this class, we're going to talk about universe. What is this universe? Where do you get one? How much does it cost? Is it free? How big is the universe? Something you might have debated with friends. Is it bigger than your own mind? Is it bigger than this classroom? Or is this classroom really the only thing that exists? What is the largest thing in the universe? Is it your brother's ego? Is it something else? What's the smallest thing in the universe? How old is the universe? The last one has been addressed more accurately than ever before, just in the past decade. These will all be covered in much detail during this semester. So this is a bit of a teaser for what we will learn this semester. However, I will give cursory answers right now because people's curiosity tends to fade after about 5 minutes. That's the disadvantage of the web. I think it's shortening people's attention span, so that if you don't see anything clickable or interesting in about 5 to 10 seconds, you're looking for another web page. So we're trying to give little snippets of information here, like addressed to the modern information age attention span. Here's some answers. There are many definitions to universe. Many years ago, it was just whatever town you lived in, or there were rumors that, more than rumors, people knew there were other towns nearby. But pretty much your universe, your effective universe, was your town. Some people thought the universe was essentially flat. Now we know that the Earth, for instance, is not flat, and that if you look at towns far enough away, you can't really see them, partly due to the curvature of the Earth, not only to do with things on the Earth like mountains. But the definition of universe has changed. As technology has advanced over the past 3,000 years, the universe then grew to be the spherical Earth. And for a while, the Earth was thought to be the universe. Then other planets, which were known to be points in the sky, were discovered to be planets like our Earth. And so the universe became the solar system. Then it was slowly realized that those things on the sky, those are stars. And those stars are just like our sun. So the universe involved all those stars. And the universe moved out to become our galaxy, which is 100 billion stars. And for a while, although since technology increases at an increasingly fast pace, these epochs go smaller and smaller in time, shorter and shorter in time. So our galaxy was the universe, and then there were other spiral nebulae out there, and it was gradually realized that there were many galaxies like our own. And that incorporated an even bigger universe. And that happened within the past 100 years. So we went to thinking that our own galaxy was the entire universe, to knowing that there are lots of galaxies out there in the time period of your great-grandparents. And a lot of this is explained at the Wikipedia entry. So what is the size of the universe? Well, okay, we define different types of universe now. There is something called the visible universe, which is as far out as we can see. As far as light can get to us from it, that's the visible universe. So if you can see it, it's in the visible universe. There may be things even out there past that. It becomes a little bit philosophy, although we do have some measurements as to what could be out there. But the further out you go, there could be the entire universe. And there could be things called brains, causally connected brains or causally disconnected brains, B-R-A-N-E. That compose the universe, and maybe what we see is the collision of two brains. But we don't know that for a fact. What we do know is there's lots and lots of galaxies out there, and these galaxies appear to be moving away from us. And the size of the distance that we can see is about 13.7 billion light years, although we actually get into debate exactly what you mean by size, but we're going to leave that alone right now. So light from 13.7, light that left things, objects, diffuse objects as it turns out, 13.7 billion years ago, is only arriving at us now. So that is the size of our visible universe. What is the largest thing we know? The largest thing we know is getting debate as to what you mean by largest thing. So the largest thing, is it the universe itself? Well, sort of. But one definition for largest thing is something that's held together. And there's ways of holding things together. So we're held together by electromagnetic phenomena. But things are held together by gravity. For instance, our solar system is held together by gravity. And our galaxy is held together by gravity. And there's clusters of galaxies that are held together by gravity. And as it turns out, that there are clusters of galaxies. And once you get bigger than that, the expansion of the universe doesn't allow local gravity to hold it together by gravity anymore. So by one definition of large, the largest thing there is a supercluster, and that's 100 million light years across. And by light year, I mean time it takes light to cross. It takes light 100 million years to cross from one side of the supercluster to the other. What is the smallest thing, one might ask? Good question. Really fun to ponder. Small things could include there are things so small we don't know. As I'm fond of saying, there's typically 3 numbers in astronomy. Those numbers are 0, 1, and infinity. If the number is 1, it had a finite size, and we measured it and we said it's 1. So for instance, my height is 1 human height. The size of this room is 1 classroom large. So we know how large it is, and we measured it. It's 1. There are things, however, so small we don't know how small they are. And one of those things is the electron. We don't know how small an electron is. It's so small that every time we try to measure it, it's smaller than that. So sometimes we say it's 0. That's another the number of in astronomy. But 0 really means in astronomy we don't know how small it is. It's too small to measure. There's also too large to measure, and that's essentially infinity. The photon is too small to measure. Neutrino, too small to measure. There are other fundamental particles that we don't know that are too small to measure too. So how small are things? We don't know. Too small to measure. How old is the universe? Well, recently we've been able to measure the microwave background radiation. What's that? Well, we'll be talking a lot about that during this course. Way back when the universe was really young, things were just being pulled together gravitationally. And there were sound waves echoing through the universe. And the universe is pretty uniform, but much hotter and denser. The universe suddenly became clear, and light was able to fly through it. So that light came to us. And due to the patterns on the microwave background radiation, we see a surface way out there. By looking at that surface in detail, we can now estimate the universe is just about 13.7 billion light years old, which is how I got the size of the visible universe also. Before, only about 10 years ago, we would have said the universe is maybe 10 to 15 billion years old. So even during your lifetimes, astronomy has advanced notably. So we now know a lot more about the universe than we did even a few years ago. Again, reviewing, light year is a unit of distance. Even though it has the time year in there, it is how far light goes in a year. An object 1 light year away, seen as it was 1 light year ago. So it sounds philosophical, but you can only see the past. Everything you look at, light had to take time to come to you from it. So when you look at yourself in the mirror, light bounced off you, took time to bounce off the mirror, and then came to your eye. So you're not seeing yourself in the mirror as you are right then. You see yourself as you were, a fraction of a second ago. And as we look at the sun, we don't see the sun as it is right now. We see the sun as it was about 8 minutes ago. And we see the nearest star as it was about a year ago. And most of the stars you see in the sky, you go outside and you see stars at night. Most of those you're seeing as they were maybe couple hundred years ago. The Andromeda Galaxy, maybe 1 million years ago. Things like that. Fun trivia, light could circle the Earth about 7.5 times in 1 second. So light is really fast. It's not infinitely fast, though. And because it isn't, we know a lot about the universe. So again, to learn more about light year, you can go to the Wikipedia entry. And now, a brief calculation, because there will be some calculations in this class. The speed of light is well known now to be 3 times 10 to the 8th meters per second. So here's a question. If the sun is 8 light minutes away, as I said, how far is that in meters? Well, the answer is, to use very introductory formula, distance is equal to velocity times time. This is it in equation form. D is equal to c, where c is the velocity, this time the velocity of light, given as c times time. So this is the velocity, 3 times 10 to the 8 meters per second. This is the time in minutes, but minutes and seconds don't match. So we have to convert minutes to seconds by this multiplier. And we find out that the sun is 1.44 times 10 to the 11th. This is 10 to raise the 11th power. Which means 1. This is exponentiation. If you're not aware of that, look that up. 1 followed by 11 zeros meters away. So I'll speed up. We're running a little slow here. Visible light. Light is more colorful than we can see. You might know this acronym, ROY G BIV, red, orange, yellow, green, blue, indigo, violet, which is some of the colors in the visible spectrum. There is an infinite number of colors in the visible spectrum. There's more colors there than you can see, but we've named some of them because that makes us happy. Visible light typically runs from the very red to the very blue. Visible light, well, almost visible light, you can go outside. There is light more red than you can see. It's called infrared light. And even more red than that, there's microwaves and there's radio waves. So the stuff you listen on your radio actually is very, very red light. So red your eyes don't record it. We can go in the other direction and say, you know what, there's light more blue than you can see. Past violet. And past that is ultraviolet, X-rays. So when you go, let's say, to the doctor from your recent skiing accident, worried that you broke your arm, the doctor will likely have, a technician, illuminate your arm with X-rays. X-rays are so powerful, their light's so blue, that they pretty much go through your skin, no problem. But they don't go through your bones, no problem. Therefore, they can get an image of your bones and see if it's broken without actually cutting open your arm to see if you're if your bone is broken that way. Gamma rays are even more powerful than X-rays, but they're so powerful they go through your bones, so they don't make good pictures. That they're not very useful for taking pictures of your bones. Different people and different animals perceive light differently. Many times I'm asked, what is true color? You know, what is the real green? Everybody's eyes are slightly different. Your vision of green is different from my vision of green. Your computer monitor, every computer monitor displays green slightly differently. So there's a comedy of errors here, and there is no true color. We can make guesses, but it's all approximations. Next, our sun is green. Now, is this because everybody's eyes know? If the sun appeared green from the surface of the Earth, then we would know it, because there's so many people who would report a green sun, it would just be written up, and it would be on Wikipedia as green, and even if somebody went back and changed it to yellow, the green people would win out, because that's usually what happens. The sun is really green because it's actually yellow-green, because the blue light that makes the sky blue has been scattered out from the sun. So if you were to take all the blue in the sky and smush it back into the sun would be more green. So the sun is actually yellow-green. It turns out that our Earth's atmosphere scatters away blue light more efficiently than it scatters away red light. That's why the sky is blue. And that's why the sun is green. And more information, you go to electromagnetic spectrum, a good Wikipedia entry. All right, so here's how you see stuff. Radio waves, our eyes, you essentially need a detector as big as the waves to see things. Radio waves can have wave sizes of centimeters to meters, so you need big telescopes. This is the very large array of radio telescopes in Arizona. And I think this is a trailer here. Shows you the size of these things. I once had the good fortune to walk around in one of these discs, not one that was in active use. Later they were pissed. No, I was invited there. And so you can walk across. It doesn't even take a minute. It takes less than a minute. Don't go near the edges because you'll slide. These digits all of these things create a very large baseline and are able to see the sky in radio light. Radio light makes it through our atmosphere, so we're good. You can make radio telescopes from the surface of the Earth. Humans don't have radio eyes because it's more efficient to have eyes near the center of where the sun emits its light, which is near the red-yellow band, so we can survive. Jets from a radio galaxy. This is a radio galaxy called 3C296, which is the third Cambridge catalog entry 296. So we're going to be reviewing all this stuff in the class in some detail, but here is a galaxy. Here are jets from the galaxy, and these jets are emitting radio light that we're seeing with radio telescopes like the Very Large Array. This is microwave light. So we went from radios into the microwave. This is the entire sky. So you look out at the sky, and here's one direction, and here's the other direction. And this sky is very cold. It's actually about 2.7 degrees Kelvin, which is even colder than 2.7 degrees Celsius, which is even colder than 2.7 degrees Fahrenheit. But due to very accurate, microwaves don't make it down from to the surface of the Earth very well. So you need to put satellites in orbit around the Earth to see them. So the Wilkinson Microwave Anisotropy Probe, WMAP, did that, among other instruments, COBE before it. It turns out that some microwaves do make it down to the Earth's surface, and they can be seen best near the South Pole. But generally, you're better off above the Earth's atmosphere. It's just so expensive to go above the Earth's atmosphere that you have to make a relatively small detector. But we'll talk about that during the class, too. Okay, here's infrared light. If you go outside and you look up and you try to find around here in Houghton and in dark places, you can see the band of the Milky Way. It is spectacular. If you go outside and look up and you let your eyes dark adapt, you not only see lots of stars, but you can see this band that goes across the sky. It's a light band, and it's the Milky Way. If you had infrared eyes, though, you could look out and you could see, or if you're above the Earth's atmosphere, you could see actually where the center of the galaxy is. We can't see it in visible light. There's just the band that's the whole disk of our galaxy. But in infrared light, you can see the millions, even billions of stars that occupy near the center of our galaxy. This is a visible light image of the Coma cluster of galaxies. This is a relatively nearby dense cluster of galaxies. So This is a galaxy not unlike our Milky Way galaxy. This is probably more massive than a Milky Way galaxy. Almost all the spots you see on here are not stars, they're galaxies. And each of these galaxies have billions of stars. So our sun is not unique by a long shot. There's lots of galaxies that contain stars like the suns, and there's even clusters of galaxies. You know, so galaxy, 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 galaxy. You get it. It's a vast universe out there. Going past the visible into the ultraviolet. This is what our sun looks like in ultraviolet. Our sun's pretty constant for stars, otherwise life would have had trouble developing on Earth. Some stars are not so constant, not good places for life to develop around. However, our sun is still active, and it's easier to see the activity in the sun typically in the ultraviolet. So here in ultraviolet light, you can see activity areas on our sun here, and dark areas where there's magnetic depressions. We'll talk about our sun in some detail later. Okay, this is an X-ray picture of a supernova remnant. So a star here, I'm not sure which star, it might have been this one, but I'm not sure, exploded in a spectacular explosion. Our sun will probably not go supernova, but massive stars will, and they throw out the entire out part of most of their mass just out into space. And so here we see, and they then glow in X-rays for a number of reasons. There's radioactive elements there that continue to decay and cause an X-ray glow for thousands of years after a supernova explosion. This is a very recent picture taken from the astronomy picture of the day on August 28th. This is the gamma ray sky as seen by a very new, very powerful gamma ray observatory. It used to be called GLAST, but it's actually now been renamed as Fermi, who's a famous physicist, previously known as GLAST for people who knew that name. And you can see several things on the sky. You can see the band of our Milky Way galaxy here. You can see a faraway center of a galaxy called a blazar there. You can see a pulsar, a rotating star that's super dense here, the Vela pulsar, and there's other pulsars too. So our knowledge of the universe is changing even since a few days from the beginning of this class. However, GLAST is not yet made this gamma ray sky was pretty well known even before GLAST, but GLAST will get images of the gamma ray sky that have never been found before, we hope. And that will be really cool. So we'll see the sky in a new way and discover it in a new way. So the sky at night. If you go outside, you notice the band of the Milky Way galaxy. Most of the stars you see outside are near our sun. They're within, light takes within couple hundred years to get here from there. Most of the stars in our Milky Way galaxies are further than that. It takes thousands, tens of thousands of years, hundreds of thousands of years to get here from your average star, even in our galaxy. But the bright stars you see, they're relatively nearby. The brightest stars we see, the brightest star in the sky is called Sirius. It's in a constellation of, well, it's near the constellation of Orion. Probably the most popular star in the sky, and a star that's always visible when it's clear nighttime in the northern hemisphere, is called Polaris. Polaris is actually not all that bright. Sirius is much brighter. But Polaris is always up. It never sets. There are constellations. Orion is a constellation that many people have probably seen. The Big Dipper is an asterism, not a constellation. There are a certain number of constellations that are recognized. The asterisms are not those. The Big Dipper and Little Dipper are asterisms. So the Big Dipper is one of the asterisms. The Little Dipper has Polaris in it. Actually, the Big Dipper points to Polaris. We'll see that in a bit. Also, the brighter stuff you see many times on the sky not only is the moon, of course, but Venus and Jupiter can become very bright. So can Mars. They can be unusually bright, brighter than any star. And the band of Milky Way that I've mentioned a couple times already. These are things you see when you go out without any telescope or anything. You just go out and appreciate the night sky, which there's a lot there to appreciate in my biased view. So here we have the constellation of Orion right here. Hard to see. Here's the 3 stars in the belt of Orion. I missed the third one. Let's try that one. Let's clear that. This is Sirius. This is a comet which isn't normally there. This is a comet Hale-Bopp, which appeared in 1997. I might have my year wrong. I'm getting my comets confused. This is the Pleiades star cluster, which we'll talk a little bit about. This is on the ground. It's the fisheye image. Here's a tree. You can also notice that there's stars of slightly different colors. If you look at stars for a while, you can notice that some are more red than others. Mars has a distinctly red hue. By the way, for people involved at Michigan Tech, we will be dragging if you look in the hall, Fisher Hall, there's this big thing that sort of sits there and you have never seen it used. It can be used. It can be dragged out onto the deck of Fisher Hall. It's a 25-inch student telescope, and we're going to try to have some student nights where we drag that out and see things like, planets or the moon in some detail. Okay, so here's a picture of people camping out, looking at the night sky, looking for meteors like this one, but something they don't have to. This is the Big Dipper right here, part of the Big Bear Ursa Major. So I circled them now. I'm going to clear it so you can see it. Most people, I think, who even are not into astronomy, can identify the Big Dipper. Although I worry that people who are going outside and looking at the night sky less and less, even Orion and the Big Dipper, are becoming strangers to the average person. 100 years ago, when we didn't have so many lights, or almost any lights, people were quite familiar with many asterisms and constellations of the night sky. Nowadays, less and less. Many of the planets, here's a bunch of planets. They don't line up like this every night, but here, this is the plane of the ecliptic. So on this particular night, right at sunset, you would have been luckily able to see Mercury, Venus, Mars, Saturn, and Jupiter all lined up right here in the ecliptic plane. And people knew it was coming, of course. It wasn't a surprise, and so many people went out. This might have occurred in 2002, although sometimes we rerun images and seen all of those together. During this semester and other semesters, there will be meteor showers where the Earth moves through the stream of a comet or an asteroid that left debris orbiting the sun. And when that happens, you get to see streaks of light that last less than a second, typically. This is a time image photograph where you see many, many streaks of light. So you wouldn't see all these. This is the Perseids, as captured, I think, last year. Really cool to see. Takes some patience, but I will advise you when ones are coming up. It'd be fun to go out and just get like a lawn chair or a sleeping bag, as we saw a couple slides ago, and watch for them. Okay, so I'm going to review some APODs today. Today I'm going to be reviewing September 1st through September 3rd. Again, if you've lost track of the website, you want to go to apod.nasa.gov. Okay, so let's see if I can do that. So here's the Blackboard learning system. Here's something. Here's the what is this picture. This is the astronomy picture of the day for September 4th, 2007, so last year and a day. So the Martian, we have two rovers rolling around Mars right now, Opportunity and Spirit, and they're robotic. There aren't people on them driving them. They're sort of driven by remote control and through computer interfaces from the Earth. And this is a big crater, Victoria Crater, that one of the rovers has rolled into in order to study the history of Mars. Was Mars wet? What kind of rocks were on Mars? What is the history of Mars? And how does that affect knowing the history of our own planet, the long geologic history of our own planet? Okay, so if we go to September 1st, okay, this is a picture of a CG4. It's a ruptured cometary globule. This is CG4 right there. It looks like it's going to eat this galaxy, but it cannot. That galaxy is far, far in the distance. And this gas cloud, almost all gas clouds are right in our galaxy. So it is gas clouds like these, cometary globules, from which many times stars will form. So gravity is pulling these together, and stars are forming in there. Why this? There's many things we don't know. Most globules are roughly spherical. This one seems to have ruptured, and it seems to be open-ended. Why that is, we don't know. There's lots we don't know. And that's why we're always taking more and better pictures of the sky in many different ways, trying to find stuff out. Because sometimes when you learn something, you learn that you don't know it as well as you thought you did. Okay, this is so again, what you're responsible for is the explanation and not the links. The links go deep. The links are fun to follow. If you don't know something, you can follow the links that will tell you more. This is an elliptical galaxy called NGC 1316. It's Elliptical galaxies are usually they appear as ellipses on the sky, which is why they're called elliptical galaxies. This elliptical galaxy is interacting with this spiral galaxy, and that's why it has unusual dust plumes there, which are unusual for elliptical galaxies. But this deep exposure is showing something more interesting. It's showing these unusual features here. One of the things we've learned in the past decade or so is that galaxies are actually very complex, and they've interacted with many other galaxies. And they've left streams of gas, dust, and stars strewn about in unusual ways. And we've found that our own Milky Way galaxy has a bunch of these itself. Our own Milky Way might have a disk where stars rotate, but it also has all these other strange wisps and plumes of stars and gas out there. So that helps us understand how our galaxy formed. And the last picture of the day you're responsible for is this picture of our own planet taken by the Deep Impact Space Probe, one of the many spacecraft, several spacecraft that are floating through our solar system. Many times they will buzz Earth and download data. In this case, this was able to buzz the Earth as the moon was passing it. And so here you see sometimes what's called a double planet system, but it's really the Earth and the moon. The moon isn't really a planet. Here's the Earth and here's the moon, and you can see the moon superimposed on it. And you can see some features on the Earth and the moon. So this is today, in fact. This is today's astronomy picture of the day. So if you just go to apod.nasa.gov, it redirects you to this site. So to learn more about this and all other APOD images, which is one of the good reasons I think why APOD is good for teaching, in that if you see an image and you don't understand it, you can read the caption, and if you don't understand the caption, you can click on the links in the caption, and eventually you'll understand, hopefully. If not, send email or ask your friends. Okay, so the next time we will meet will be, this class will meet in session will be next Monday, and we will release lectures also next Monday. Please come to class, and please submit questions based on the class, and those questions may be used, hand them out at the end of class. Those questions may be used in quizzes and in midterm and in the final. So until next time, I'll see you then. Class. Although there is if you're taking this at Michigan Tech, there is reason to come to class because, as I will show in the syllabus, if you bring a question about, or you formulate a question about the material and you hand it in during class or after class, would be appreciated. That question may be incorporated on the quiz or on the midterm or the final. So there is value in coming to class this year. But if you're following this from Kansas or China, or you just don't want to be bothered to come to class, which is fine, people are busy, you can just download the lectures from iTunes or Learn Out Loud. You can take the quizzes online, and you never have to see me again. And if we pass in the hall, you can just look the other way, pretend you don't know me. That's fine. You can still get an A. It's happened. So I usually start the lecture out with a picture of something that is not obvious what it is. One of the neat things about astronomy is that it's a big universe out there, and we don't know what much of it is. And so there's some really interesting pictures that are taken, and it's interesting to just contemplate what is that. And so I will start almost all lectures, including this one, with a what is this, where I just show you something, as you see on the screen. And maybe if you're an astronomy buff, or if you've been following the astronomy picture of the day, okay, everybody ready? Hello, and welcome to the introductory lecture for introductory astronomy at Michigan Tech. It's called Physics 1600, PH 1600 for people who are into letters and numbers. So this is the first class. Today we'll be doing a tour of the universe. But first we have boring stuff to talk about related particularly to the courses taught at Michigan Tech. I will say that these lectures are being recorded, And as within the past 2 years, these lectures are generally available over the internet. They're available over iTunes, and over the past couple of years, they've been available at a website called learnoutloud.com, and it's no breaks, and it's spelled as it sounds. And so I've gotten email from places like China and Kansas from people who have followed versions of this course. And it is partly because of that audience that I'm going to be doing the course in the way I'm going to be doing it this year, which is making it free in the sense that it doesn't cost anything to buy the materials for the course. This is going to be an entirely online contained course. So you never have to come to a or something. You might know what it is, but I will tell you for an extra fee, and I will tell you for free during the class were you to watch the whole lecture. If I forget and it looks like I'm wrapping up, please feel free to raise your hand and tell me. So I said, this lecture is Grand Tour of the Universe. There's lots of preamble today. So if you're watching this on the web, move the little slider across so you don't have to listen to this, this boring stuff. This university is Michigan Technological University, which is in the beautiful Keweenaw Peninsula of Upper Michigan. I'm your cosmological coordinator, Professor Robert Nemiroff. There will be 2 TAs, at least, as I know them, to help with this class. Both are undergraduates, Ashley Ames and Martin, and I have never pronounced his last name, although I've seen it many times, Boulette. Okay. And this is happening live right now, for me anyway, in the fall semester of 2008. A big change with the past way this course has been taught is that there will be no formal book. We're going free this time. So the Wikipedia pages on astronomy, particularly introductory astronomy, are really good. So we're going with the Wikipedia pages, and I will list exactly which ones they are. Now you might say, I know what to do. I'm going to go to that Wikipedia page and change it to one word which says blah, and then all I'll need to know is the word blah. But that won't work, because what you're responsible for is the Wikipedia pages as they appeared yesterday. So going into Wikipedia and editing it now won't work. Now how do I get to yesterday's page? If you type in astronomy into Wikipedia, you're brought to the current page. However, if you go into history, which is one of the tabs on Wikipedia, you can find out the page that is closest to yesterday, occurred before yesterday, and that's the one that you're responsible for. There is going to be very little changes. Most people aren't going to go in and try to make big changes because of this little puny class. So you're probably okay. But if you have any questions about the material, if you think you're seeing something on Wikipedia that's not right, go back to the September 1st or 2nd page. If you still have continued questions, what you want to do is you want to send email to ph1600@mtu.edu. There will be people monitoring that web address all the time. PH stands, this is the title of the course. PH1600 is the Michigan Tech designation for the course. So I have access to that email address, but I'm too lazy to monitor it that often. The TAs have access to it, and they will be monitoring it more often. If it is above the TA level, if it deals with something, a question they can't answer or something like that, they will alert me to go there and look at it. So, so I will ultimately be responsible for what's there. You'll see that address many times. If you're taking this course at Michigan Tech, you have to go to courses.mtu.edu. So if you're a freshman just learning that, a lot of your courses you'll find online there. They will have syllabus, plural of syllabus. They'll have other wonderful things that I can't even mention here, partly because I don't know what they are. We can do that right now with the miracle of modern technology. We can go to the Blackboard learning system here, and here you notice up at the top it says courses.mtu.edu. That's where you go. Then you're going to be asked for your Michigan Tech login and password. If you don't have one of those, I'm not the person to ask about that. You need to find your faculty advisor or some really smart kid at the end of the hall who seems to be well connected and ask them how it is they're getting into the Michigan Tech pages. Then they'll tell you, and then you can pretend after that that you've known it all the time. That's what I do. Let's go to the syllabus here. Page contains both secure and non-secure items, so please beware. Let's display it anyway.